In this video, we're going to polish off chapter 1. So this is the last video of chapter 1. There's a couple concepts that I want to go over. They are important concepts, but in terms of practicing them, these are not all concepts that we're going to work a lot of lengthy exercises on. Some of them are things where the concept is valuable, the techniques are valuable. The calculations, though, are more effort than what you possibly do. And also the calculations are something where usually you're going to be dominated by non-ideal effects anyway. However, some of the concepts we talk about in this video are going to become something where when you're using an actual op amp doing an experiment, you can fairly effectively measure some of these parameters, measure some of these features. And then once you've measured those, you can use that to better model your op amp. So, but these are techniques, concepts that are important to know. They're just not, I'm just warning people in advance, we don't do a lot of actual numerical calculations with these. You're not going to have a lot of homework problems on these. So it's not necessarily something that we're going to do a lot of examples of as we go through in this video. So let's talk about how loop gain alters output resistance and input resistance. So the first, we talked about this a lot, or not a lot. We talked about this briefly in previous videos, and input output resistance is always something that you can measure by finding the relationship between input current and input voltage, or finding the relationship between output current and output voltage. So you can always find it that way. However, the whole idea of us doing the feedback model and developing this concept of loop gain is it lets us, we don't have to go through those calculations over and over and over again. So how does loop gain alter output resistance? Let's start with that. Well, loop gain improves output resistance. It improves output resistance by a factor of 1 plus L. That means for situations where you expect to see high output resistance, so for instance, things like shunt output, things like current output, right? If you're producing an output current, you'd expect a high output resistance. In that case, loop gain actually increases it by a factor of 1 plus L. For things where you'd expect a low output resistance, things like voltage output, if you expect a low output resistance, loop gain decreases it by a scale of 1 plus L. And it's fairly easy to see how that works if you look at two actual design examples. So, or not how that happens, I should say. Let's look at two design examples. So these are two, I just Google searched headphone amplifier circuit, and I found two examples of a headphone amplifier circuit. And they're probably too small for you to see. I can barely see them on a 4K monitor. So yeah, I don't know. It might be dicey. You can zoom in on YouTube. But basically, I want to highlight two things in these designs. And we're not going to go over the whole design, but there's two things here. Both of these designs have a resistor connected to the output of the op amp. And you might say, why do you have a resistor? Why would you add a resistor in series with the output of an op amp? Well, what's going on here is basically this resistor is designed to protect the op amp. So there's this issue where, normally if you're designing with an op amp, the op amp has a certain internal output resistance, and that output resistance offers some protection to the op amp against sort of blowing itself up, right? So basically, you want to limit the current that an op amp outputs. If you have too much current output of an op amp, it's going to overheat, it's going to destroy itself. Some op amps have a certain amount of self-limiting current in the fact that they'll have some output resistance, but a lot of times it's not enough. Usually if you're designing an op amp, you want that thing to have as good a performance as possible. You want it to have as low of an output resistance as possible. And you're generally going to leave it up to the person designing to limit the output current. You're going to give some spec to say, make sure this op amp never outputs more than 40 milliamps of current. If it does, it can damage the op amp, the end. It's the person who's designing with that op amp to actually make sure their circuit doesn't exceed that output current. Well, one challenge comes when we're designing consumer electronics products. Like with a consumer electronics product, you have no idea what the end user is going to be plugging into any port of that product. As I know in this particular example, my kids had these laptops. I got them these cheap little throwaway laptops. I have two daughters. I don't know, people might not know, but I have two daughters. They're both in elementary school. And I bought them a year ago, these cheap, like throwaway little flip style tablets. And one morning, one of my daughters woke me up at like 6 a.m. You know, she'd gotten up to watch YouTube videos at 6 a.m., which is what kids do these days. I'm probably a bad parent to let my kids watch YouTube. I don't know. All right, don't report me or don't think less of me for that. There's a lot of things to think less of me for, not for that. Anyway, she wakes me up at 6 a.m. and says, "Help, my laptop won't charge." She said, "I plugged my charger in, it's not charging." And I'm, of course, thinking, well, it's a cheap throwaway laptop. It's probably just that internally the little charger came disconnected. They do that. It's probably what it is. And sure enough, I go out there and she's got the power plug plugged in and the light's not turning on. It's not charging. The battery's dead. Yeah, it seems like a dead laptop. I take this into the office. I use state resources to repair my... I'm really going to get in trouble here. I use state resources to repair my family's laptops. I bring it into the office. I measure the output voltage of the power supply. It looks good. It's outputting 17 volts or whatever it's supposed to. So then I start disassembling the laptop. I start taking the screws out of the back of it, start taking it apart. And then I think to myself, I think I remember when I was using this laptop, I think I remember the power plug being plugged into the other side. Why is it now plugged into this side? Turns out the laptop had a 3.5 millimeter power plug and a 3.5 millimeter audio jack. And what was happening is she and I can't blame her because I was doing the same thing. We're plugging the power plug into the audio output because it fit, right? If it fits, So we were plugging it into the audio jack. Well, of course, you plug a power plug into an audio jack, you're shorting the terminals of the audio jack. So there's this problem of you never know what idiot, with a PhD might be plugging into your audio output of your amplifier. So they'll add these resistors to basically it's a way to make sure that even if some idiot plugs in a power plug into the output of your headphone amplifier, that it doesn't destroy the amplifier, it doesn't destroy the op amp. But there's two different ways of doing this. So if you look closely at these examples, one of these circuits connects the feedback path after this current limiting resistor. And one of them connects the feedback path before the current limiting resistor. Now, both of these ultimately will limit the op amp outputs because, whatever current the op amp outputs, there's not that much going through the feedback network. The current it outputs has to go through that resistor one way or another. But there's a very big difference between these two. So in this case, where this 10 ohm resistor is inside the feedback loop, feedback is actually going to clean this up. Basically, you're feeding back on the voltage on the other side of that 10 ohm current limiting resistor, which means by this, that 10 ohm resistance is actually going to get reduced by a factor of 1 plus L, which could be, that could be thousands, right? So to this circuit, it's going to behave not like a 10 ohm output resistor. It's going to behave like, a 0.01 ohm resistor. And that means that the output voltage will still be the same or pretty much the same, even though we added that 10 ohm resistor. So people might say, well, how, come on, how if it maintains the same output voltage, how is that actually protecting the amplifier? Because you have to think about what it has to do to maintain the same output voltage. In this case, as current starts to flow, this op amp is going to produce a much larger voltage across this resistor in order to produce the correct voltage of the output. So essentially, the op amp itself is going to have to output a bigger voltage in order to maintain the proper voltage at the output terminal. So what's going to happen is before this op amp gets to the point where it puts out too much current, it's going to rail. So basically, this output here is going to rail, is going to hit the rail of the op amp supply. And then once that happens, this signal on the other side of the resistor is going to clip. So basically, this design will give you a perfect, your output will clean up that output resistance doesn't really matter. It's going to mostly get cleaned up by the feedback, but you're going to increase your chances of clipping. So once you do go over current, it's going to start clipping that output. This approach here doesn't do that. This approach here, the only valid signal is right here. So basically this output is going to be the correct value, amplified value. And then it's just, your headphones connect here and the headphones are in series with a 20 ohm resistor. So this circuit is the same as literally just putting your headphones in series with a 20 ohm resistor. We're not correcting the signal on the other side of that 20 ohm resistor. But actually, this is probably okay too. Because if you think about it, right, if you have a headphone, you know, the headphones, it's pretty much a constant 8 or 16 or 32 ohms. Having an extra 20 ohms isn't going to necessarily change the audio that you hear. It's going to change the volume of what you hear. So this design at the top is kind of more likely to, it's less likely to clip, but it's more like it'll just get quieter as you start to get closer and closer to exceeding the current limit of the op amp. So it's two different approaches, two different design ideas, but the idea is basically output resistance that's inside of the feedback loop gets cleaned up by the feedback loop by a factor of 1 plus L. And again, if this were a current drive instead of a voltage output, it would be increased. The impedance would be increased by a factor of 1 plus L. You want current supplies to have a high output impedance, as we talked about in video 1 or so. Okay, and so what the takeaway from this general concept is open loop gain is often far more important than ideal output impedance. So op amps are able to clean up their output impedance by having a good open loop gain. Open loop gain still remains the most important parameter for having a good op amp. Well, linearity can be more important, but that's, yeah. Okay. But again, there are limits, right? You know, again, there are limits for power applications. So ultimately, internal resistance, even if the op amp can clean it up, it's going to ultimately limit the maximum current the op amp can output with it outputting the full rail voltage. So, okay, what about input resistance? So input resistance, sorry, oops. So input resistance, very similar. So input resistance also gets improved by a factor of 1 plus L. So in series, it's improved by 1 plus L. In shunt, it's improved by dividing by 1 plus L. So again, for current input, you want to have a low input resistance. For voltage input, you want a high input resistance. And you know, loop gain helps that in both cases. Now, here's an interesting thing in the shunt comparison. So basically, when we are comparing a current, so we're taking current comparison at the input, where the current is produced by that feedback network. The equivalent input impedance is a function of the output resistance. This is an important concept. Now, this is true of the. This is sort of true of the inverting topology, right? It's true of these sort of inverting shunt comparison topologies. This is really important. That basically what's happening is if I'm this input, I am feeling at my input both this value and this value. What's more important, some portion, right? Again, it's highly diminished. It's reduced by 1 plus the loop gain. But an important parameter here is this is not just resistance. And we're showing resistance, but this is actually true for impedance. So if there was some capacitance output here, you know, if there was some capacitance to the output of the op amp, this input signal would be seeing a portion of that capacitance. That can be very important. That's called the Miller effect. And the Miller effect results, you know, usually the Miller effect is most important for what it means for capacitance. But what it means is the output capacitance of an amplifier circuit can show up at the input of the amplifier. This has really big implications for cascaded amplifiers. A lot of times what we want to do is we want to say, let's do a gain of 10 amplifier followed by a gain of 10 followed by a gain of 10. And one issue with Miller capacitance is the input to this cascaded set of amplifiers will be still seeing the capacitance of the very output. So it's you will get the features of the output of this cascaded amplifier network will still show up at the input, which can have undesirable consequences for your circuit. Okay, now we're going to pivot to a really, really, really big concept, and there's the concept of feed-through gain. So far we've basically only looked at op amps, or the analysis we've done so far, which is called two-port analysis, is looking at networks as sort of a forward gain and a feedback gain. That's not actually a full description of these systems, though. There are signals don't just pass through these op-amp networks by traveling through the open loop gain, and traveling back through the feedback gain. You also have some signals that travel directly from the source to the output of the network. And that's as a result of the input to output being a connected set of resistors. So in the ideal case, this signal gets nuked by the input assumptions, by the terminal assumptions. But in the non-ideal case, that's not true. So we actually have some what's called feed-through gain. So feed-through gain is this extra signal that passes directly from the input to the output. And it's important to model. Well, sometimes it's important to model. In some systems, this is a very important parameter. In some, it's not necessarily that important. So what we're going to do is we're going to now take a different way of looking at op-amps. And it's called return ratio analysis. And it's basically a more thorough way of modeling an amplifier system, which allows us to take into account this feed-through gain. So basically, instead of having just a model that looks like this, we are now developing a model that looks like this. And as a result, we no longer sort of refer to the loop gain. We use this letter T to refer to the return ratio, is what it's called. It's a similar concept to the feedback, but it allows us to take into account more elements of the op-amp design. The equation looks very similar, though. So we have sort of this, instead of the ideal gain times 1 over 1 plus 1 over L, we now have ideal gain times 1 over 1 plus 1 over T plus this feed through attenuated by 1 plus T. And and again, we will talk about this. We will talk about this T return ratio more. Okay, so feed through gain. How do we identify feed through gain? Luckily, this is one of the easiest things that we analyze in this class. Feed through gain is fairly straightforward to identify because feed through gain is determined by the limit as the gain of our amplifier goes to 0. What is a gain of 0 amplifier? A gain of 0 amplifier means that basically this produces 0 volts. So when this little guy in here produces 0 volts, what's happening? It's basically grounded. So if we take this, now keep in mind, as we identify feed through gain now, we are using a more complete model for the op-amp. We are now including output resistance and this sort of input differential resistance. And so cleaning this up, if we want to identify feed through gain, we essentially ground this internal amplifier, and then we just draw the network of resistors. So in this case, we have our input voltage passes through resistor R1, and then we have RD in parallel with a series combination of R2 and R out. And V out is sort of this voltage now across this R output. So we can remodel this using the circuit shown here. And all we have to do to find the feed through gain is to find the ratio of the output divided by the input. And in this case, and usually the way we find this is by doing this collection of cascaded voltage dividers. So basically, if we wanted to find V out as a function of V in, personally, I would just use the voltage divider analysis. So I would say, V out. So let's find the equation for this node here. This node here, using voltage divider, would be V in times R1 divided by R1 plus, sorry. So V in times, it's going to be the resistance of all this. So it's going to be RD in parallel with R2 plus RO divided by RD in parallel with R2 plus RO plus R1. Now this is where the book sort of shortcut way of writing this. The book would divide both sides of this by this big old monstrosity up here. So they would basically So the book would do that, right? So we do that once, and that's the expression for the voltage here. Now, the voltage here divided to produce the voltage here, what's that going to be? The voltage here divided to produce V out is going to be, one more time. So we're taking the voltage here, which is this whole thing, times, now it's going to be 1 over 1 plus oops. 1 divided by 1 plus R2 over RO. So now this whole thing, and now again, so this is V out equals this whole thing. Divide both sides by V in, and you get this big giant expression here. And cleaning that, it's a lot of it ends up, if you're trying to keep it numerical, if you're trying to keep it the actual, variables, it becomes a kind of a big ugly thing. But you can also, if you're given actual values, it's a lot easier. You can just plug these in and just solve this along the way if you're given actual values. So you're not always given that, so you got to be careful. Okay. So that's how you find the feed through gain. And so again, going back to our equation here, so to do this analysis, we have to find feed through gain. We also have to find this return ratio term. Okay, so return ratio, also known as return ratio loop gain, but this is not the same as, it's related to, but it's not the same as loop gain. Return ratio loop gain is basically, if you think about the loop gain was the open loop gain times the feedback gain. That's basically but what we're doing here, but instead of saying feedback gain, which sort of implies the circuit between the output and the input, we're now just doing what's called the return ratio, which is basically taking into account anything that can diminish a signal as it goes from the output, from the, anytime a signal, anything that can diminish a signal as it goes from here inside the op amp to here across the front of the op amp, anything that can diminish that diminishes this return ratio. So this can take into account this output resistance. It also takes into account the effect of the feedback resistances, and it can also take into account this input resistance. And in this case, we can even model our input supplies as impacting this too. So series resistance in our supplies will also have this effect. Okay, and mathematically, this is the return ratio is going to be negative A, where A, this is little a, is still the open loop gain of the op amp itself, times this ratio VD over VT, VD being this voltage across the differential voltage across the terminals, divided by VT, which is sort of this test voltage that we insert internally. We basically, it's this test voltage that's applied to the other side of the internal resistance inside the op amp here. So that's what that is. Okay. Trying to see okay, yeah. So how do we measure this? How do we actually, I kind of implied it, but how do we actually perform a test to find what this ratio is? Well, it's very similar to before. Before, when we were finding the feed through gain, we sort of took the ratio of the output to the input. We're kind of doing the same thing here, but we're taking the ratio of the input to the output. We're sort of going in the other direction. But we can sort of do the same thing. We can basically do a voltage divider from the output. We can do a voltage divider from this voltage down to produce this voltage over here. So, okay, and so this negative here, basically, normally you don't have to worry about that because your feedback signal normally goes to the negative terminal of the op amp. So if effectively the negative and the open loop gain A, as long as your feedback path is going to the negative terminal, all you're really solving for is this, how much this output test signal gets divided as it goes from the output back to the input of the op amp. Okay, so here is an example that we showed here. this is how we would set up the circuits to test these. So this is this would be the circuit to test the this would be the circuit to test for the return ratio, and this would be the circuit to test for the feed through gain. So, and a lot of students often express questions about sort of how do you generate the equivalent circuit. So really, it's just a matter of in this case, sometimes for finding this return ratio, you need to separate, you need to break the circuit right at the output of that dependent supply internal to the op amp, and you then hook up a test voltage here. And then the basic rule is all of the other supplies are just set to 0. So voltage supplies are open circuits, current supplies are short circuits. Sorry, current supplies are open circuits, voltage supplies are short circuits. And then you basically just assemble the collection of the circuit, keeping in mind, right, that these ground symbols are all connected, right? So it's all, might as well be that if you're analyzing the circuit. Okay, so what if we actually, wanted to calculate this? What would we actually do? Well, this one is, so again, if we're trying to find this VL as a fraction of VS, so we have a series connection of resistors here, and then we have these two parallel connections. So the voltage here, so finding an intermediate expression for the ratio of this node here to VS is going to be given by sort of that right side of the voltage divider equation. So in this case, that would be, if we're using the book shortcut, right, it'd be 1/1 plus, right. So that would be our expression to find this voltage. And then that expression would be, we'd have to do that divider again to find VL here. So that doing that divider again, this would be 1/1 plus R2 divided by so this whole thing, this whole ugly thing, assuming I didn't flip those, it's embarrassing if I flip those upside down. Let me make sure. I feel like I did one of these wrong. No, I think that's right. Yeah, so that big ugly thing, again, it's just a lot of ugly voltage dividers. So it's voltage dividers, a bunch of stuff in parallel. So you're going to have to sort of refresh your memory on that, things in parallel, things in series. But it's not too bad. It's, it's fairly straightforward to do that. Similar analysis for here, right? So this ratio of RD over VT, we're basically finding this, what fraction of VT makes its way back to this output here. So that's kind of what return ratio is all about. So in this case, you would have, RO in series with this in parallel with this whole thing here. And then once you found the expression for that, you do another voltage divider to find the voltage here. And then you do another voltage divider to find the negative of the voltage across here. But again, the equation is -A times blah, blah, blah. So just be the divider. You can see if you look in the book, this is partially why we don't do a lot of these to completion. These are massive equations of things in series and parallel, or of things in parallel and voltage dividers. So the book even condenses them, but it's not complicated stuff. It's just a series of repeated voltage dividers. But if you're trying to keep it in terms of these variables, it gets very big, very fast. If you're given actual numbers, it's really straightforward. It's really easy. And so this is basically how we'd model an op amp more completely. So if we wanted to model an op amp more completely, we could use this. We could use this return ratio and feed through gain, and we could develop an expression that much better represents the actual gain, the actual closed loop gain of our amplifier than we could simply using the model that has forward gain and feedback gain. So another benefit of using this idea of return ratio is return ratio gain is really good for finding impedance. So Blackman's impedance formula is a technique we can use to find the impedance between any two terminals of a feedback amplifier circuit. That is incredible. We can take any two terminals and apply a test to find these two parameters, the short circuit circuit return ratio and the open circuit return ratio, and we can find the equivalent resistance of our between those two terminals. So again, it's not just the output or input; it's any collection of two terminals. We can do this. There's a procedure, right? So basically, we need to find these terms. The procedure is so R naught is the equivalent impedance between the terminals with the gain set to 0. So previously we talked about what is a gain of 0? It's an op amp that produces no output. So basically internally we can ground that dependent supply inside the op amp, and we can just find the equivalent that way. And also with amplifier removed, input output resistance is still modeled, and setting all sources to 0. So setting all the sources to 0, open current supplies, short voltage supplies. To find the return ratios, we basically do a standard return ratio analysis, which we talked about here, which the return ratio analysis is, you break the circuit right here, you disconnect that, and then you apply a test voltage, assuming we had some test voltage applied internally here. Then you find this ratio of what portion of this test voltage appears across the differential terminals of the op amp when you after you make that change. And we do it twice. We do it once with the terminals with our whatever two arbitrary terminals we want. We do it once with them short circuited and once with them open circuited. And then this is our equation that gives us the equivalent resistance between those two terminals. Now, a lot of times if you're doing this analysis, a lot of times one of these is going to be 0. So for instance, if you're doing the output resistance, almost always one of these terms is going to be 0, except for very exotic circuits. So let's do an example of using Blackman's impedance formula. Now, one thing I want to note is Blackman's impedance formula also very powerful for finding equivalent impedance, for real equivalent impedance. But as I said at the beginning of this lecture, a lot of times the value of this is not so much in calculating it from scratch using data in a data sheet. A lot of times the value in this is measuring these parameters experimentally and then having this powerful equation that we can use to model the system. So, okay, so looking at, I guess it's kind of already drawn, right? So looking at what circuit is this? This is the non-inverting amplifier circuit. So looking at the non-inverting amplifier circuit, doing an analysis, Blackman's, so this is the sort of Blackman's impedance formula, Blackman's equation, sometimes it's called. Doing an analysis on this standard case of the non-inverting amplifier, first of all, we can find the R naught. So R naught is, and we'll do this for the input resistance here. So we'll do this analysis for the input resistance. We could have done it for the output resistance, right? We could have done it here if we wanted to, but we're not gonna. So using the input terminals to find the equivalent impedance, equivalent resistance between those two terminals, we have initially to find the R naught. R naught is going to be, again, we just take this, assume this gain of this op amp is 0. What is a gain of 0? It means basically, gain of 0 means this is grounded. So basically, I'm making a mess here. So basically replace this with a ground. And so then so doing that, this is your equivalent circuit. It's fairly straightforward. How do we find this? So we're looking for the equivalent input resistance here, equivalent input. Now this is not a, for doing the, for doing Blackman's impedance formula, this R naught calculation is not quite the same as the feed through gain calculation. So we're not looking for a ratio. We're literally looking for the equivalent impedance right now. So we're looking for the equivalent impedance this circuit sees with a gain of 0. So in this case, it's just we're not going to do voltage dividers. We're just going to do combining resistors. So it's RD is in series with R1 in parallel with this whole thing. So plus R1 in parallel with, and this whole thing is R2 plus R naught in parallel with RL. And I should say R0 because we're it's a little messy. So basically yeah. Okay. Alrighty. So yeah. So hopefully that's the same. Shoot. No, that's not the same. Why is that not the same? Do I disagree with this? I think I disagree with this. Maybe I'm wrong. I don't think so, though. I think weird. Well, either I'm wrong or the book's wrong. I probably should have tested this video before I created it. Okay, but that's the process. 70% chance it's right. So now we find the return ratio short circuit and open circuit. So the return ratio short circuit basically, or let's start with the return ratio open circuit. So for calculating the return ratio open circuit, we leave these terminals open. So now here's the thing with the return ratio open circuit, with these open, we're looking for the ratio, right? We're looking for this difference between this voltage here divided by this voltage here. But what do we know about this voltage here for the open circuit case? Well, when this is open circuit, there can be no current flow through RD, which means there can be no voltage, which means the open circuit return ratio has got to be 0, which is reflected here. What about the short circuit return ratio? Short circuit return ratio, we're going to short that terminal. And now what do we have? Now we have basically, if we're trying to represent the negative of this voltage here as a function of this voltage here, what's our circuit now? We have our test voltage. So why do we say V test, right? Because all we're looking for is a ratio. It doesn't matter what this test voltage is. If you want to actually do it numerically, you could choose 1 volt or whatever, I don't know. But ultimately it doesn't matter what this voltage is. All we care about is the ratio. That's why when I do the voltage divider, I really only do the ratio resistor part of the divider, because the output equals input times that ratio. Well, I mean, it's that ratio that I care about there. That didn't make sense, but. So I'm just reconstructing. I'm taking the circuit and I'm flopping it over and I'm reconstructing. If you don't trust my redrawing, just do a node by node analysis. Just do, okay, R naught touches R2 touches RL. Okay, yeah, R naught touches R2 touches RL. Okay, and then so R2 is then going to be, so you can do, okay, is R1 in parallel with RD? Yes, it is. Does R1 Does this node that touches R1, R2, and RD exist? R1, R2, and RD, yes, that node exists, you know. So there's ways to check to make sure your equivalent circuit is the correct equivalent circuit. But now our question is, what's this voltage here? As a ratio, what's this voltage here divided by this? So basically, what fraction of VT is this voltage across RD? So it's just going to be voltage dividers here. So basically, we can find the expression for the voltage here. That's going to be 1 over 1 plus R naught divided by RL in parallel with R2 plus RD in parallel with R1. Why did they say RD? I'm worried I have the wrong equation here. Don't think I do. Oh, sorry, no, RD. Yeah, that's right. What am I doing? I think in my mind I was adding something like that there. No, that's right. We got it. R2 plus RD in parallel with R1. Yeah. Okay, we're good. Yeah, so that would be the expression for the ratio voltage here. Then we'd have to do it again to find the voltage here. So then I'm doing another voltage divider would be that expression times, it would be 1 over 1 plus, we got R2. And then we just have RD in parallel with R1. So we do one voltage divider to find the expression for the ratio here, and then another voltage divider to find the expression for the ratio here. That's it. That's what they're doing here. And then, of course, it's negative A times the ratio of the RD divided by VT. Or sorry, VD divided by VT. The negative goes away because, again, we were solving for this voltage at the negative terminal, which is the, so the negative goes away. We're negating the negative, it goes away. And then, of course, we have to multiply that through by the open loop gain to get the return ratio. So clear as mud, folks. But this is the process that you go through. The good thing, it's not fun because we have to build these equivalent circuits and we have to do a lot of resistor stuff, but it's very powerful. So once you follow this process and find these parameters for your circuit, you have a very powerful equation. You have an equation that tells you the equivalent resistance of this entire thing. So, okay. So that is the return ratio model and Blackman's impedance formula. And we will refer to these later on. You're not going to have a whole lot of homework problems going over these, but we will refer to them later on. So thank you for watching this video. I will see you next time.